I'm bothered, right? Yeah, I don't have to, which is something like well, yeah. We don't know. I didn't. It should be under half. Yeah. Assuming that we can just continue to find out. Yeah, I see the point here.
Okay, folks, tomorrow's the review session for exam number 3. It will take place not here, but actually right across the hall. One of the biggest taking some. So what we're going to talk about today, this is the last new section before the exam, is orthogonal projections. So let me kind of set you up a little bit. Last time what we talked about was projecting a vector y on the some vector u, right? And what do we do? How do we go about this? Well, we let the sun shine down perpendicular to u. We call this y. On u. Right, and we had some dot product formula that this place. Now, what we're going to try to do here, our scheme now, is to do something more general. So let's call this W. This is a vector that comes out. Well, actually, it could be even in W1. So what are we going to do? We're going to do something like, instead of projecting this vector onto this vector, notice this is sort of a one-dimensional analog. You're projecting in the plane this one-dimensional subspace generated by you, this line, and projecting y down onto this. Instead of projecting it just down onto onto the line, what if W is a plane or a three-dimensional space or something even bigger? So I can't really do this for higher dimensions, but I can try to illustrate this way. What we're now looking for is what we call y hat. And this is the vector projection of y on the subspace W, right? This is our scheme, or our quest, that is, to find projection of vector y on the subspace. Okay. So what do we know about y hat? What should this be? So what can you say about y hat? It should be a unique vector in W such that y minus y hat by the way, on this picture, where is vector y minus y hat? Where is that? How do we figure out what y minus y hat is? Well, I don't know much, but when I add y minus y hat to y hat, which is here, I should get y. And what's the relationship, just from this picture, what's the relationship, y minus y hat and w? It's orthogonal. Right, the way I've drawn this picture, every vector in W, y minus y hat is perpendicular. Right, so y minus y hat is in W part. Remember what this is every vector in space, in all of space, that is perpendicular to everything in W. Anybody notice something else about what something else must be true about this y hat thing? Notice something about a relationship between y hat given y. This relationship. What's the relationship among all vectors in W? Maybe this one, maybe this one. What's true about the distance between y and y hat?
Isn't it cosine?
Yeah, but you're trying to be too fancy. Really just state it simply. This y hat, because of the fact that this is perpendicular, is the vector in W that is closest to y, right? If you make it a little bit longer, it's got a little bit longer distance, right? If you put it in another direction, it's much longer distance, right? So this is two things that's true about this y hat, this projection. Number one, y minus y hat should be perpendicular to everything. And number two, y hat is actually a solution to a minimum problem, right? Because it is actually the vector that is closest. It's the vector in W is closest to my vector y. What do you suppose happens? Anybody want to, given that last statement, what do you suppose happens if I was such a Dorcas Malorcas that I drew y already in W? What do you suppose y hat would be? It would be y itself, shouldn't it? Right? Because that would be, if it's already in W, then it's already the vector that's closest to itself in W. Okay, so let's dig deeper on this. So let me let's do this one first here. There. I'm gonna go ahead and dive right into it. We will see why this is true. This we call the orthogonal. Orthogonal decomposition theorem. Let W be a subspace Rn. Right. Then each y and Rn can be written uniquely in the form y is y hat plus c with y where this piece lives in W. And Z is in W. I'm not done with the theorem yet, but I just wanted to say something about this at this point. So first thing, take any subspace you want, any subspace. Then every vector in all of Rn can be written in this way. You can break it down as a piece in W plus a piece in W part. So what is true about Y hat and Z? They must sit at right angles. So this generalizes that physics stuff I was talking about. Remember how I was talking about, oh, you can take some vector and you can take it apart into orthogonal components. This says that you can do this more generally, right? If you have any Y in Rn, you can break it down into this piece right here. One piece in your predesignated W and another in W part. So these two are orthogonal to each other. By the way, just gut check. What happens if Y is in W in the first place? What would Z be? Zero, right? And notice 0 and Y, I don't care what it is, perpendicular. What if Y is 0? Then in that case, the Z would be Y, all right? Let me add a little bit to this, because what is more than just that statement? I can give you sort of something that's even a little bit computational in the following sense. In fact, theorem, if U1, U2 up to UK is an orthogonal basis, for W, then I'm going to show you how to build both of these pieces parts here. Then Y hat, the piece in W, and this should look familiar. UK over UK, UK. See exactly how to get this orthogonal projection. In fact, this gives you the formula for the orthogonal projection. You just take, how do you build the orthogonal projection? Just take Y and dot it with every element of your orthogonal base. Divide out by that and just multiply it by this. And you're going to think I'm cheating here because that's what I am. Right, that's a big fat cheat, because certainly if that's true, then Z plus Y hat is equal to Y, right? And for notation, so terminology. Y hat is sometimes referred to as orthogonal projection. Of Y on the W. Okay, so there's the formula right there. Right. By the way, I'm gonna show you what this is true. And this will be computationally useful for us because it'll sort of show us how the computations work as well. But before I do this, anybody want to criticize my theorem? There's kind of well, there's a potential gaping hole. It turns out it isn't, but if I were you, I'd be a little concerned.
There's two vectors that satisfy that.
Oh, yeah, what are they?
The negative one.
Ah.
The negative of y would be the same.
Okay, that's a point, but I sort of consider those two vectors to be sort of the same equivalent because they're on the same line, right? But what did I assume I have over there after the in fact statement? Yeah, isn't that statement there on the in the middle board on the left side? Isn't that assuming that I have an orthogonal basis? I mean, I do know this much. Well, we know so far in the classes if W is a subspace, it has a basis. Agree? Oh, no, it's got an orthogonal basis. Yeah. Yeah, but so for example, I mean, if I just give you the basis of some five-dimensional space, how do you know? So if I give you this, if I give W this, some such. Yep, that's the one you're doing. Now, if I look at this basis, the span of this is a vector space of dimension 3 inside R5. Everybody agree with that? Is this orthogonal? Well, I'll make this up on the fly, so I doubt it. The dot product of these two is 3 minus 2 is 1, and 8, 9. Already these two are not at right angles. Right here, I get 9 minus 4 is 5. It looks to me like none of these are at right angles, right? This dot is -3. Does this space have an orthogonal basis? Yeah.
Divided by the length. Take them all like 4.
Well, right, but that's not going to change whether they sit at right angles or not, right? Yes.
Well, if it's a three-dimensional space, there must be at least some three vectors that are on.
Intuitive, but essentially you're correct, right? So notice Rn has an orthogonal basis. Can anybody tell me what it is? How about E1, E2, E3, all the way up to here, right? In fact, that's an orthogonal basis, isn't it? Well, what about this randomness? In fact, we're going to discuss this later after this exam. It turns out that every W that you can have in here will have an orthogonal basis. And let me kind of at least intuitively show you why that's true. If you have a one-dimensional subspace, it's clearly got an orthogonal basis, right? Just take the vector that's not 0. No problem, all right? Okay, well, now let's suppose we go to 2 dimensions. Is that vector by itself a basis of this plane? No, because you've got 2 degrees of freedom, right? How could you find another basis element? Well, here's another basis element here. Is that an orthogonal basis? No, but what you could do is you could project this vector onto this one. Now these two are an orthogonal basis, right? What if you've got a 3-dimensional space, right? Well, I already know I've got an orthogonal basis inside of here. right? Suppose I've got a third vector. Right? This doesn't look orthogonal, right? This sits at right angles, this doesn't sit at right angles to any of these. These two already in the plane sit at right angles, but this doesn't sit at a right angle. Well, again, do the projection. And now this vector, and this vector are all at right angles. Everybody okay with that? So you can just actually, this is not approved by any stretch of the imagination, but you can just keep building up like this. So in fact, we're always good to go on this. So here's the big orthogonal decomposition is basically given a subspace W, it's got a W perp, and you can take any vector at all and decompose it as something in the original space, maybe even zero, but something in the original space with something that's orthogonal to that. Let Y be as defined here. And let Z be Y minus Y. Now, the first thing is note that Y hat is in W. Can somebody tell me why Y hat is in W? It might be important to look at what Y hat actually is. Yeah.
Because Y had you written as a linear combination.
Absolutely. Notice this is just number times U1, number times U2, all the way up to number times UK. Right? And these U1 up to UK is a basis for W. Hooray, I win. So Y hat is a linear combination of the basis elements of W. So it's in W. Everybody agree with that? Okay, that's step one. Let's see what we've got torn up here. Checkamundo. Let's check this. I want to prove that Z is in W part. How do I do that? How do I show that Z is in W part? What is the meaning in the first place for Z to live in W part? Okay, right. Let me put it in a more simple-minded way. Z must sit at a right angle to everything in W, right? So as he says, the dot product with anything in W has to be zero, right? So all we have to do is show that Z is at a right angle of every basis element of W, right? So to accomplish this, we show Z dotted with UI is zero. For all these basis elements, right? Because if Z sits at a right angle to every basis element, it's in W part. Everybody agree with that? Okay, well, let's just do it. What's Z dot UI? Well, Z is this thing. Agreed? And what can I do with this? What's true about the dot product? Yeah, I can distribute out. Good. Y dot UI minus y hat dot ui. Now I want to focus on y hat times ui. Let me kind of take a little bit of an aside here. Gosh, what a mess that is. Y dot U1 over U1 dot one U1 plus Y dot UI UI dot UI UI plus Y dot UK UK dot UK UK. Now, dotting with UI. So when I dot UI with this, what happens when I dot U1 and UI? What do I get? This is an orthogonal basis. So when I dot any two different U subscripts, I get 0. Agree? So when I dot UI with U1, 0. UI with U2, 0. UI with UK, 0, right? The only survivor is this term. And I get this. Everybody agree with that? This is the only survivor right here. Everything else is killed in battle. You see any way to simplify this? Right. This number is the same as the denominator, right? Because remember, this is number, right? So I get y dot ui. Let's get back to our adventure, shall we? This is y dot ui minus, when the smoke cleared, I got y dot ui. Oh, I'm getting excited here. 0. So Z is orthogonal to I. All of them. So Z is in W part. And there we go. Check and move it over. So what have we shown? We've shown that we can write y as y hat plus z, because to solve for this, you get y as y hat plus z, with y and w and z and w part, just like that. I feel a little dirty, like I've almost gotten away with something here, right? But I mean, it's not too bad, right? There's actually technically one more thing that I need to show. Does anybody pick up on this here? What's another claim that's sort of, I didn't scream it from the rooftops, but it's in here somewhere. Well, no, that's given to me, so I'm good with that. That it's unique. Wonder why it's unique. Well, let's write it 2 different ways. This is actually kind of interesting. And again, it'll feel like we've sort of gotten away with something. Let's suppose that we can write it 2 different ways. Here, y1 and y2 hat are both in W, and z1, z2 hat vector are in W part. Well, if I manipulate this a little bit, I get Everybody agree with that? This is just. Y1 hat minus Y2, Z2 minus Z1, right? Everybody agree with that? So this means. This means that these two vectors live in both W and W part. Right? Why does this, because they're equal, right? Notice Y1 minus Y2 is in W, right? Because subspaces are closed under addition and subtraction, right? But this is also equal to this thing, which is in W part. So this thing is both in W because of the way it's written, and also because it's equal to this, it's in W part, right? Same with this. This is written because of the fact Z2 and Z1 are in W part, it's here, but now it's also in W itself. Do I agree with that? What vectors are in both W and W part? What's true of any vector that lives both in W and W part? That is correct. Why is that? It's a vector that must be perpendicular to itself. Note, if V is in W and W perp, then V is perpendicular to itself. Correct? And what does it mean for a vector to be perpendicular? What does it mean for two vectors to be perpendicular? The dot product must be 0. So I can only conclude from this that V dot V is equal to 0. And what does that mean about V? It must be 0. So what does this mean? It means that Y1 minus Y2 hat is the 0 vector. So Y1 and Y2 are the same. It also means that Z2 minus Z1 is the 0 vector, which means Z1 and Z2 are the same. So there's your uniqueness. There's only one way to do this. Okay, any questions on that? Okay, questions? Okay, so here's another theorem. This one is kind of, sometimes you want to maximize and minimize certain things. I mean, if you're in engineering or really any kind of STEM, optimization problems, that is finding a max, min, some kind of optimal solution is often very, very important. So here is kind of a optimization problem this solves. Theorem. This is called, we call this best approximation. Let's let W be a subspace of Rn. And Y a vector in Rn. So Y hat is just this thing we've been talking about, it's the orthogonal projection. This. So then y hat is the closest vector in W to the vector y. So this orthogonal, this projection vector is the vector in the subspace W that is as close as possible to y. That is the norm of y minus y hat is strictly less than y minus W. W and W, but it's not y. Okay. So in other words, so I'm going to let you, I'm not going to go through proof of this. The proof of this is really basically it's Pythagoras' theorem. That's it. But I will draw you kind of reiterate a picture here. So let's imagine that W is this. We got some crazy Y flying off at an angle in the space. This is what we call Y hat. And what this theorem says is basically because this sits at a right angle here, because y minus y hat sits at a right angle plane, that this actually minimizes the distance among all the vectors in the plane. I'm sorry, in W, of all the vectors in W, this y hat here is the one that is closest tip to tip from this vector y. And you can see actually that that this must be a minimum in the following sense. If you move this vector just a little bit, make it a little bit longer in any direction, you actually get a distance here that's bigger than the dotted yellow distance. Everybody agree? And like I said, you can use Pythagoras' theorem for this because you can couch this D as the hypotenuse of a right triangle, right? And the hypotenuse is the longest side. So this distance D from the slightly perturbed vector is bigger than the perpendicular distance. So it's a little bit farther. Everybody okay with that? Questions on that? That's essentially the guts of the proof right there. Okay. Any questions? Okay, so there's one more thing that I would like to tackle here. And this is actually not that surprising at all. Theorem. Suppose that W is a subspace bar N. And suppose W has orthonormal bases. By the way, somebody remind me, what does it mean to be orthonormal? It's orthogonal and what was
length one.
That's right. So it's a little bit better than orthogonal in the sense that it's still orthogonal. Every basis element sits at the right angle to all the others. But also I've sort of trimmed it a little bit so that all the vectors have length one. So suppose that this has an orthonormal basis, and I'm going to call it something here. U1 up to UK. Then this y hat we've been talking about looks like this. Y dotted with U1, U1, but Y dotted with U2, U2, Y dotted with UK. And if we build the following matrix with orthogonal columns, by the way, what kind of columns does this matrix have? So I built the columns out of the basis elements. So what's true about the columns of this matrix here? This matrix has orthonormal columns, right? What do we call such a matrix? Orthogonal? Evil professor tricked you. Not necessarily. Yes, we would call it an orthogonal matrix if it had one more property. What's that? It has to be square, right? This matrix up here, it's not necessarily square. So I was being a little bit kind of tricky there. But if this would be an orthogonal matrix if it has the equal number of columns, then y hat cross y is equal to u transpose times y. I'm going to let you all work this one out. I'm going to work a quick example for you. See if you can work this out. It's not too difficult. By the way, can somebody explain why right here we're not really saying anything? There's nothing really different than what we've done before. I mean, this looks like a brand new formula, but it really isn't. Somebody tell me why?
You're saying the columns, or the vectors in the basis are linear combinations?
Well, so the real formula, if you will, have this. If you look at the old bit, I've already given you this formula for orthonormal basis, right? And we had those denominators. Everybody agree? So, but what's true of these denominators now? They're just one because of the fact this orthonormal, these are all equal to one. But so this is just collapsing an old formula into something that's smaller, more convenient. There's no real big content here. Okay. So I'll leave you with just one simple example. Any questions about it? Let's see if I can. Yeah. Yes, right, I guess I need to come up with something. What's the home? 0. Actually, let me get up. Let me make sense last time. Got it. Let's see, so let's do this. Okay, so. Okay, so let's look at the span of these two vectors, right? This is subspace part 3, right? Notice that if I call this U and V, what's the dot product? 3 minus 4 is -1 plus 1 is 0. So these two vectors, even though it's not clear just from writing the numbers down, until you do the dot product, these two vectors are orthogonal, right? So, somebody give me another vector.
Too far.
Let's figure out what y hat is. Well, what it should be is, it should be y dot u over u dot u times u. Y dot b over b dot b. So let's figure this out. It's something times u. And u was 1, 2. And something times something from b, which is 3 minus 2 is 1. Now I've just got to figure out what numbers to put here. What's y dot u? I think it's 11, isn't it? Am I agree with that? Or what's u dot u? In this case, it's 6, I guess. Right? Okay, what's y dot b? Looks like it's 9, right? And what's b dot b? This is what, 14? I can figure that out if I want to. Trust me, I can add pricing, but I'll just leave it like this. But this vector right here is a linear combination of these two, so it's in W. And that would be W. So let me ask you this. What would happen? Well, so what would happen if what would happen if we had picked Y already perpendicular to this space? So somebody gets 3, 2, 4, right? But what if somebody had picked a vector that was actually already perpendicular to this space? Would have been 0. You would have gotten 0, right? That's correct. You would have gotten 0, 0. Okay, any questions? Questions? Okay, don't forget the review session tomorrow, 5 o'clock, right across the hallway. You'll have one more quiz before the exam. Well, let me think about that. You might have a quiz. Yeah, you'll have a quiz. The exam.
You cannot.
Shoot that afternoon, Friday. Yes.
Yes,
Are your Friday office hours this week gonna be interrupted?
this week. No, I don't think so. Yeah.
Just planning ahead.
Okay.
For sure. Yep, I'll see you then, or I guess we'll talk about it.
Sounds good.